Today we're going to talk about QR algorithm, and this is the algorithm that we will use to compute eigenvalues of a given matrix. Here in this part the algorithm is being described. A is the matrix that you would like to find its eigenvalues, and first we assign it to A1 because of it would make the notation easier to understand. So okay, we have like a for loop, and in each, okay, so we start at I equals 1 and A1 equals the matrix, right, that we are inputting, and then in each iteration we are computing like Q and R. So using this QR decomposition, and QR decomposition basically for a given full rank matrix, we are computing Q and R such that Q is an orthogonal matrix, R is an upper diagonal matrix, and there is also one important thing to point out here. R, by choosing the diagonal entries of R matrix, this upper triangle matrix, positive, we can make this Q and R unique for a given A matrix. We can make this, right? So for a given A, there might be like multiple, of course, Q and R matrices. So this is not like a unique operation, right? But if we can impose the condition that the diagonal entries of this R matrix are positive, then this is unique. For a given A, Q and R can be found in a unique way. Okay, so after that, now we have the Q, we have this similarity transformation, and then we assign that to A I plus 1, and then we basically iterate, like doing the same operation. And one thing to point out is that, okay, Q is orthogonal matrix, we know that, plus since A is full rank, Q will be also full rank and it will be invertible. So this is like a proper similarity transformation, and because of that, the eigenvalues of this matrix and this matrix, they are equivalent, right? So the set of eigenvalues do not change. This operation preserves that. All right, so that was the QR algorithm, but the important point is that why do we know, or why it works, and how do we know that, like for example, there's a iteration going on here, right? And like we said, n, we can make n 10 or 100, it depends on the application. However, the important point is that how do we know that it will converge, and how do we know that it will work, right? So this is the main problem. And so this is the source, a simple proof of convergence of the QR algorithm for normal matrices without shifts, Michel Schatzman, and it is easy to find this on the internet, right? So let's go with the proof. And by the way, this will be the first video that I have this, I'm using, for example, the dark background. I hope it would work out in the end. So let's start. So for a given matrix, we can express it such that X, D, X inverse, and X is what we call model matrix, right? So basically, eigenvector or matrix whose each column is populated by an eigenvector, right? So for example, anyway, let's not talk about like unnecessary issues here. D is a diagonal matrix, and such that each entry on that diagonal line corresponds to eigenvalue of the given A matrix. All right, so this is like, we are familiar with this, right? Let's call it equation number 1. And then, okay, and again, one more assumption here is to facilitate the proof process. I am imposing the constraint that yes, this is what's going on. Okay, yeah. for all I not equal j. So basically what I'm saying is that let's call magnitude each magnitude of each eigenvalue or is unique for a given matrix, right? We do not have two eigenvalues such that their magnitude are same, right? So we don't have that condition, or we are ignoring such cases. Okay, that's in my opinion, this is a reasonable starting point. So having that assumption in mind, right? I mean, one could also argue that anytime we have this is a very pathological case, and one could even argue that this is numerical computations are concerned. Let's say it will be very rare that we come across such matrix. All right, saying that, let's continue, and we can express model matrix. Again, this is its type of QR decomposition, right? Q times R, and such that R is upper triangle and Q is orthogonal, right? So again, this is what I said. This can be done in a unique way by choosing R entries on the diagonal line of R matrix positive. If we have that condition, then this is unique. All right. So let's call it equation or expression 2. And here let's look at 3. This is inverse, having the condition that A is full rank, X will be full rank, and X inverse can be found, right? And here this is AU decomposition, this is lower triangular and upper triangular. We know what that is. So let's continue. I haven't stated anything that is interesting so far, right? So we have QR decomposition and we have AU decomposition for given X and X inverse. What was X? X was model matrix for a given A, right? Let's continue. So, okay, this is the first interesting statement here. Let's call lemma 1, and Q inverse, or rather, let me just say, okay, we know what Q is. Q is this, when I say Q, basically the QR decomposition, Q that we find by conducting a QR decomposition on the model matrix for a given A. Okay, so here we have the A, and we are doing this similarity transformation using Q. Okay, so the statement is that, okay, this matrix is diagonal. And okay, so let's try and understand why that would be the case. So we know what that is, right? We are basically expressing, okay, this comes from statement number 1, right? Okay, and by having this substitution, we have this expression, right? And then we are expanding this term, and this is what we will have. Okay, so now we're basically doing this, right? And then this is what we have. Okay, so here let's look at RHS, right hand side, and I hope I didn't miss anything. All right, so this is what I'm looking at, and R is upper triangular, right? And R inverse is also upper triangular. This comes from the fact that upper triangular matrix, or for example, if you multiply two given upper triangular matrices, what you will end up with will be upper triangular matrix. Okay, so having that plus D is diagonal matrix, and again another information is that upper triangular times diagonal, the result will be upper triangular. Okay, so at the end this right hand side term is upper triangular matrix. Okay, so that means that this term, which was the first term given here, this will be upper triangular matrix. So, okay, wait a sec. Is it diagonals? Oh, that was a mistake. That was okay. I wanted to say upper triangular. We are correcting typos. So, okay, let's check this remark. If we can find such Q, right, and we can find the set of eigenvalues for a given A, such that like we have this Q and A is the given matrix. So since we know that this is upper triangular, some type of triangular, what we would do to compute the eigenvalues of a given some type of triangle or like a diagonal matrix, we just look at the entries on the diagonal line, right? So this is what we would do in that case. And all right, so let's continue and let's check this definition. So first of all, remember, let's check the algorithm one more time. We have given A, right? We will be updating A matrix, but given A, we have this Q terms, right? So we will have Q1, Q2, dot, like it will go on like that. And so these Q terms come from the algorithm. So it's defined in the algorithm. Okay, and we are defining PI, right? And this is basically the definition. This is like, I'm not making any like statements. And since we also have this QR decomposition, we will have, since we have Q terms, we also have R terms, corresponding R terms for a given A and QR decomposition. Okay, and in each step, when we do QR decomposition, we are doing in a way that it is unique. What do I mean by that? We are conducting this QR decomposition by imposing the constraint that entries on the diagonal line of our matrix that is to be found using QR decomposition, they are positive. Okay, so if we had a constraint, this QR terms are unique for a given A. All right, so this is another definition, UI, right? So basically, like, just be careful with the indices. That is it. Okay, so this is the statement that we are trying to prove, and if we prove that, that is it. Like, we will know how the convergence or why it converges, basically. All right, let's continue. So, all right, for example, we are looking at this and then we are inside, right? So now we have this expression and we will try to prove that. So by using the definition, so this is the statement that we are trying to derive, and here by using the definition of P, we write this, right? Okay, and then again by using the definition of U, like literally this is like from definition 1 and definition 2. Maybe I should have said, okay, this comes from definition 1, this comes from definition 2. All right, maybe that would be better, but okay, doing a simple manipulation, we factorize this right hand side such that we have Qi and Ri, and based on the definition, right, which comes or from the expression stated in the algorithm here, right? This is what we would call AI, artificial intelligence. All right, so okay, and looking at the definition, we will call Pi minus 1 and Ui minus 1. All right, so this is what we were trying to prove, so that's right. And let's continue and check another statement here. This is something that we are trying to prove now, and okay, this is the expression and which comes from the algorithm. right? Like this is the similarity transformation, and in each iteration we update A, right? Okay, so by decrementing the index, right, this is what we are left with, and then using this expression and this expression, this is what we have. And then let's continue. This expression, we can call it A1, right? By this comes from the fact that like from the definition, right? This comes from the similarity transformation. All right, we can continue. And again, looking at the definition of pi and ui, this is the expression on the right hand side. Okay, okay. So I just said something wrong. This comes from this expression basically, right? And here, this is how we write it. And then let's keep going. Now we know that is the case. And let's look at another expression that we are trying to prove. And okay, this is the term that we are trying to prove, right? And this basically comes from lemma 4. It comes from this. I'm basically writing that. And okay, so P is orthogonal. Why? By looking at the definition of P, what is P? Like Q1 dot 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 Qi, right? And each Q, we know that from the QR decomposition is orthogonal, and orthogonal times orthogonal, that matrix would be orthogonal. So P is an orthogonal matrix, right? And so what does that mean? P inverse or Pi inverse will be Pi transpose. Okay, so by multiplying from left hand side, this is what we will have, and then by decrementing the index, this is the term that we were trying to prove. So this was lemma 5. Okay, so let's continue. By the way, in the source that I stated in the beginning of this video, they don't do it that way. By like, for example, there's no such a thing as like lemma, or even if there is, like lemma 6 is not that. I basically way simplified that, right? So want to make that clear. All right, so another lemma, this is the term, and this is not index, this is like power, right? Exponent. So this is what we are trying to prove. And first of all, this comes from, let's look at this expression. This comes from lemma 3, right? Like directly, I'm just writing that. Okay, so, and then I am looking at the first two terms, and by looking at lemma 5, I am substituting this term with this term, right? And again, this comes from lemma 5. All right, so, and then I am looking at this factor, right? Pi minus 1 and ui minus 1. And so here, by looking at this expression, we can directly write this term, right? So this, it makes sense, right? And so I'm basically writing, let's call xi, and then let's call a, and xi minus 1, right? So we would know that xi is, but we would be able to write it that way, right? So this is basically what we are doing. Okay. All right. And now this is the lemma 7. This D matrix, this is like eigenvalue matrix, basically diagonal, right? And L is the lower triangular matrix, like L, from the LU decomposition, conducted on or operated on X inverse. What was X? X was the model matrix. Okay, so the statement here is this expression is diagonal, right? Oh, now I understand why I made that mistake. In lemma 3 or something, I written yeah, it was saying that diagonal, so probably I copied and pasted, but I'm glad that I changed that. Now everything's cool. So okay, I am looking at this term, right, and then limit I goes to 0 infinity. This term what we have will be diagonal, right? So basically I am writing explicitly, I'm looking at the entries, right, and this is a lower triangular matrix and this is diagonal line. All right, so here, I mean, I didn't name like x, y, or something alpha, something like that. I just said, okay, this is the result, right? I'm just looking at the jkth entry of that expression, all right, of the matrix that you would end up by multiplying those three terms, and then if you look at the indices, this is what you will have, right? And one additional statement here, maybe I should have made it like earlier, but we define D such that the eigenvalues are on the diagonal line and such that it is how, okay, was it, yeah, okay, it is in descending order, right? Descending in terms of it is magnitude, because we can also consider the case where eigenvalues are complex, numbers. Okay, so this is what we have for j greater than I greater than k. So that means here for like j greater than, this is diagonal line, this is j greater than, let's call this k, right? This k is equals j. All right, and yeah, now I got what I was doing. All right, so okay, this is the matrix. This is diagonal line. Okay, this is j, right, and j is larger than k. All right, like for example, let's say j is 3 and let's say k is 2, right? 1, 2, 3, and k is 1, 2. All right, so basically what this is saying is that we are looking at the lower portion for a given lower triangular matrix, and since like due to the definition of D, right, due to our constraint, that's how we would like to express D. But remember, we said that it was going to be organized such that the eigenvalues are in a descending order. All right, so considering that k is interesting, okay, or then ascending order, yeah, okay, got it, yes. All right, so if that is the case, and this term will be 0. Okay, so this term will be 0, and then all the entries that lies underneath that diagonal line will be 0. So that means that we have what you would have is diagonal times lower times diagonal. What you would end up with is usually lower triangle matrix. However, this is also saying that due to the structure of D, this term will be diagonal. So okay, why does that matter? Now we will see why that is the case, or that will be important. So first, let's start by the definition of this comes from, right? And then, so this is the exponents. So this is what we know, right? And by looking at QR factorization of x, this is what we have. And then again, by looking at the definition, it comes from expression 3. Now we have this. And then we are just doing a very simple manipulation, like something inverse times something. What is that? Identity. Okay, but why that matters? By considering these three terms, right? What was that? This was the term that we were interested in Lemma 7, and we claimed that it was diagonal as I goes to infinity, right? Okay, so what we have is U is an upper diagonal matrix, di, like d to the power of I, is diagonal, and then this expression is diagonal, right? It goes to diagonal, a simple, or as I goes to infinity, and R is also upper, so upper, diagonal, diagonal, upper, and if you multiply those four matrices, what you will end up will be upper triangle matrix. All right, and Q is an orthogonal matrix. So okay, let's keep that in mind. So basically we have Q, which is orthogonal, times something that is upper triangular. All right, by substituting a to the power of I comes from lemma 6 here, right? And this expression is basically the one, like final expression, right? And here, what this is saying is that we have one orthogonal and one upper triangular expression, and this equals to one orthogonal and times one upper triangle matrix. All right, so, and here, like orthogonal times upper triangular equals orthogonal times upper triangular. If we are, if we see the, okay, that is like really annoying, but okay, hopefully I didn't lose data or something. Okay, I'm continuing with all the, like, alright, we have orthogonal upper and orthogonal and upper. Alright, so basically from here we will say pi equals q, but to make this connection, I have this example. Like this is basically, I am drawing a parallel, right? And f1x times g1y, right, equals f2x times g2y. If you had that, you would, what you would write is like f1 equals f2 and then g1 equals g2. All right, so here this is orthogonal, this is upper, this is orthogonal and upper, right? So like it is, this basically does a good job of explaining that idea, right? And here this is what we have, and basically this is the proper way of writing that, and that is it. So like the proof is over, and let's summarize, or not summarize, let's remember what pi was. Pi is q1 dot 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 qi, right? We multiply all of them, and then qi is computed at the ith iteration in the algorithm. Okay, so this is how we know that the algorithm will converge, right? Like we are doing, let's go to the definition of the algorithm, and in each iteration we are conducting this similarity transformation. And what this is saying, like looking at the proof, this term AI is going to have the shape of some type of triangular matrix. And when we have that, right, and since this is a similar transformation, the first given matrix eigenvalues will be the same as eigenvalues of like ith term, right? And we will be in a position to only look at the diagonal entities. That is it. And yeah, the proof is over. I will try to upload this PDF. And thank you everyone, and thanks for sticking to it, and have a nice day. Right.